and welcome to our 12-12 class. Today we will be going over Lecture 1, Chapter 11. So please, if there are any questions or comments you guys might have about this afterwards, please email me, let me know. Make sure this information is getting across to you guys correctly. Okay, so the whole purpose of doing this lecture series, to where we're doing the bulk of the lecturing on a video, and in class we're doing mostly worked problems, is that this is a little bit more difficult material. So I really feel we need a lot more explanation, a lot more examples in class. So this is just to try and supplement that. So let's go ahead and get started. Today we're going to be looking at our different states of matter. And we're going to be looking at specifically solutions or liquids, and looking at how liquids are affected by intermolecular forces. So within each of these lectures, there's going to be learning objectives for the lesson. So these learning objectives are here to keep us all on track, to make sure that we know what is expected to be learned from here. And from those learning objectives, we will then get a worksheet to work on problems in class. So today you should be able to look at our different states of matter, give the characteristic properties of each. So if you get your given properties, you should know which state of matter, and if you have a state of matter, you should be able to give the characteristic properties. You should know the different intermolecular attractions or forces, what they are, how they work, and what substances exhibit each. So with our intermolecular forces, this is the electrostatic interaction that we talked about back in 1211. You also want to know the difference between intermolecular forces versus intramolecular forces. Then our next learning objective is to be able to identify the intermolecular forces between two molecules and or ions and compare their relative strengths. Our last learning objective for this lesson is to be able to describe how different properties of pure liquids, viscosity, surface tension, capillary action, boiling point, and melting point, are related to their intermolecular forces. So intermolecular forces is the big theme of today's lesson. So we need to make sure we have a really good understanding of those intermolecular forces and how they work. We also want to be able to compare properties, relative properties, based on intermolecular forces. Okay, so our three states of matter are gas, liquid, and solid. Our gases themselves, we talked about gases at the very end of 1211. Gases consist of particles that are very, very far apart from each other. So with this, since they're so far apart from each other, we have a great flow with the particles. So there's a lot of flow of the particles, so they flow freely. So in this case, we've got particles that have a lot of kinetic energy. So we would say that our kinetic energy is significantly greater than the attractive forces that hold them together. I'm going to put kinetic energy as just Ke. So the kinetic energy of the particles is significantly greater than the attractive forces. Because we've got so much space in between our molecules or particles, we would say that the substances that are gases are very compressible. And since these are free-falling particles that can compress and expand, they're going to assume the volume and shape of their container. And again, since these particles are so far apart, if we think about density, density is a mass over volume. So the greater your mass in a particular volume, the greater your density. In the case of a gas, since our particles are so far apart, we have very little mass in a given volume, so our density is very low. With our liquid particles are very close together, significantly closer than our gas particles. However, they still have freedom of motion, so they are going to slide past one another freely. we would say that these particles have strong attractive forces, and the attractive forces are a little bit greater than their kinetic energy. They still have a high kinetic energy, but a greater attractive force versus kinetic energy. Because the particles are so close together, they are virtually incompressible. And they are free-flowing, which allows them to assume the shape of their container, but they cannot compress or expand, so they have a definite volume. They cannot assume the volume of their container. Particles, again, are very close together, so we've got our mass term increasing here for our volume, so we have a high density. Solid, our last state of matter, we have particles that are fixed in place, that are very close together. As such, they don't flow freely. They will vibrate in position, but they will not move or switch position. Okay. In this case, we have a substance where the kinetic energy is very low, so the kinetic energy is significantly lower than the attractive forces. Okay. Again, very close together, so they're incompressible. And since they have no flow about them whatsoever, they're going to have a definite shape and a definite volume. In general, the particles of a solid are going to be a little bit closer or significantly closer than they are in a liquid. So we have the highest density within a solid. There are some notable exceptions, specifically water would be an exception versus ice. Water is going to be more dense than ice, which is why ice floats. But almost every other substance, the solid form will be more dense than the liquid form. So let us see how we're doing with our learning objective with our concept checked. So which combination of kinetic energy and intermolecular attraction results in the formation of a solid? So if we look at these, when we think about a solid, we think about something that has low kinetic energy and great intermolecular forces. So kinetic energy much less than the intermolecular attractions between particles. That's true. It's not much greater. They are not comparable. So we would say that the answer is A. So we're going to have very, very low kinetic energy, very, very high intermolecular attractions, which are holding our particles together. Okay, so let's look at these forces that hold things together. So we've got two forces. We have intermolecular and intramolecular. Let's look at intra real quick. So intramolecular means, or the prefix intra means same. So we're talking about the bonds. So we're talking about the bonds or the bonds within a molecule or compound. So we have something like water. this would be an intramolecular force. It's our covalent bond. Intramolecular. Okay? Now this has a very, very large energy, between 100 and 1,000 kilojoules per mole. We have something like sodium chloride, the bond that holds the sodium to the chlorine, sodium ion, chlorine ion. That is an ionic bond. Generally, those are a little bit greater, so that's going to be between 500 and 5,000 kilojoules per mole. Still significantly stronger than both are significantly stronger than our intermolecular forces. So because this is what's actually holding our molecule together. Intermolecular. Inter means different. So this is going to be forces that hold molecules together. Hence the intermolecular. So this is based on charge attractions. So opposites attract. So the greater that charge, the greater the force. So this would be something like this. We remember from 1211, water is a polar molecule. Therefore, it has a dipole that looks something like this, where we've got a positive end and a negative end. Positive end on the hydrogens, negative end on the oxygen. So we've got a partial positive charge here. It's going to be attracted to another water molecule. Same thing. This right here would be our intermolecular. Okay. So, as I said, intermolecular forces hold molecules together. So the greater the intermolecular force, the more the molecules are going to stay together. So the greater the intermolecular force is based on your charge attraction. So the larger the magnitude of charge, the closer, the greater the attraction. I'm going to put IMF for intermolecular force, just easier, quicker. So think something like an ion that has a full charge So that's going to have a very large charge. Something like a polar molecule. This has a partial charge. And something like a nonpolar molecule, where you don't have any charge distribution, there's going to be no charge. So if we think about these things, an ion versus a polar molecule versus a nonpolar molecule, ion's going to have the greatest intermolecular force with something else charged or partially charged. A polar molecule would be next, and then a nonpolar molecule. Since there is no charges, there is no opposites attract, and there's not very great intermolecular forces with those. So, keep in mind, as a note real quick, the state of matter, the ones we just talked about, are going to depend on a balance between that kinetic energy and the strength of the intermolecular forces. The lower the kinetic energy, the greater the intermolecular force, the more likely we're going to have a solid. As we increase our kinetic energy and decrease our intermolecular forces, we're going to go from liquid to gas. So gases are substances that have very little intermolecular forces. So the more sticky two molecules are, the more likely they are to be a solid. The less sticky, the more likely they are to be a gas. So we've talked about electrostatic forces, at least last semester we talked about electrostatic forces, and intermolecular forces are a type of electrostatic force. The equation for our electrostatic force is determined by this, or is this equation right here, where we have magnitudes of charge and the distance. So the greater the magnitude of charge, the smaller the distance, the greater the force. This is not to be confused with the dipole moment, which is U is equal to Q times by R, where the further that charge is, or the further the distribution of that charge, the greater the dipole moment. Anyways, so when we think about intermolecular forces as this electrostatic interaction, we can see that when we increase the charge on our particle or molecule, we're going to increase our intermolecular force that it can do. So always keep in mind, like charges repel, and then dislike charges attract. Okay, so keep those in mind when we're talking about our intermolecular forces. Okay, so we have got several different types of intermolecular forces. Our first one is dispersion forces, or London dispersion forces. Within here, we have ion-induced dipole, dipole-induced dipole, and induced dipole. Moving on from here, we have dipole-dipole forces. Then we have hydrogen bonding. And lastly, ion dipole forces. So these are different types of intermolecular forces. Sometimes we put hydrogen bonding under a type of dipole-dipole force, but for simplicity's sake, we're just going to keep them separate. So let's first look at our ion dipole force. So an ion, pretty obvious. This is going to be a cation or anion. So this is either a metal cation or a non-metal anion. So this is something with a full charge. And then a dipole is something that possesses a dipole, so a polar molecule. From 1211, we learned that if we have a polar molecule, the reason that it is polar is because it has a dipole. So this is a strong to moderate force. So it's between 10 and 100 kilojoules per mole. So this is the strongest of our intermolecular forces. So this occurs when we dissolve an ionic compound in water. So for instance, if we have water plus NaCl, we will get an ion dipole force that occurs. So as the sodium chloride dissolves, we produce sodium ions and chlorine ions. Right, so anytime you have an ionic solid that dissolves in a substance, what's going to happen is each ion is going to break apart so that we no longer have a bulk solid. So all of these sodium ions are going to interact with the negative portion of your water molecule. Right? And then all of our chlorine ions are going to interact with the positive portion of our water molecule. So we have an opposites attract interaction going on. And actually, this is called, what we call this is hydration, as these water molecules kind of surround our ions. And that is how we dissolve an ionic compound within water or any other polar substance. So if we have a polar substance, if it's got a great enough polarity, then it will dissolve. It will dissolve ionic compounds by taking each ion and making a hydration sphere around it. Our next force, next intermolecular force, is called dipole-dipole. So this is going to be an interaction between two molecules with a dipole. So both molecules must be polar. And this could be in a mixture or a pure substance. This is unlike our ion dipole forces. Our ion dipole forces only occur in mixtures. Okay? So what happens is the positive pole of one molecule is attracted to the negative pole of the other. So this is a weaker force than our ion dipole. This is between 5 and 25 kilojoules per mole in energy. And we see it in something like formaldehyde. So with formaldehyde, we have a structure that looks like this. We've got partial positive area here, partial negative area here. That's going to be attracted to another formaldehyde molecule, like so. And that interaction between them is a dipole-dipole interaction. Next is our London dispersion forces. So London dispersion forces, we've got 3 different types, but with each one of them, we have an induced dipole. So an induced dipole this occurs in nonpolar molecules. So what happens is we have a temporary dipole. So we know with nonpolar molecules we don't have an actual dipole, but we can induce a dipole. So we call it a temporary induced dipole, lasting for seconds or fractions of seconds. Now, this temporary dipole, though it is usually looked at in nonpolar molecules, actually does exist in all types of molecules, polar and nonpolar. So, temporary dipole, this is a short-lived dipole resulting from the movement of electrons within an atom or molecule. Keep in mind that an atom is very center. We've got our nucleus, and around it is this cloud of electrons. So electrons themselves, though they are attracted to our nucleus, they are not stuck in place. So they can move throughout our molecule. Again, remember our MO diagram, how those electrons are throughout our entire molecule. So the electrons can be pushed in one direction or another, either by coming into contact with other electrons, or coming in contact with a positive charge or something to that degree. So we can have some disturbance in that electron cloud causing a shift in one direction or another, causing an instantaneous or induced dipole to occur, where we have a partial negative charge and a partial positive charge on a molecule for an instance. because it is temporary, it's not very strong, right? So it's just a temporary shift in our electron density, allowing for some sort of induced dipole. So our first one that we want to look at is ion-induced dipole. So if we have our molecule, so something like this, so these are a bunch of carbons. So we've got our nuclei, and around that we have electrons. So we could say that here's our electron cloud around our structure. And if they're evenly distributed, then we don't have any specific area with a larger amount of electron density. However, if we induce a dipole, we get a shift of electron density in one direction or another, we can get something that looks more like this. So we have a partial negative and a partial positive because of a shift of electron density in one direction or another. Again, this is temporary. This only occurs for a small amount of time. If we have a shift in that electron density, now we have a partial positive area, partial negative area, and an ion can interact like so. So the interaction between a partial positive and a negative charge, or a partial negative and a positive charge, is an ion-induced dipole. This is a weak to moderate force. So it's going to be between 3 and 15 kilojoules per mole. All right, so not very strong. And generally what actually induces a dipole is that interaction with that ion. So ion may come in, push electron density away, and cause a partial positive area and a partial negative area. Okay. So let's see what it looks like. We're a nonpolar molecule, sodium and chlorine come in, interact, sodium pulls the electron density towards it, the chlorine pushes electron density away from it, causing those induced dipoles. Okay, then we have our dipole-induced dipole. So here we have a polar molecule in contact with a nonpolar molecule. That polar molecule induces a dipole, and we have an interaction form. So, as a polar molecule, approaches a nonpolar molecule, a shift in electron density can occur. Resulting in a induced dipole. This is a weak interaction. Between 2 and 10 kilojoules per mole. And it kind of looks like this. Let's erase that so you can see. Polar molecule, they have their permanent dipoles. And then our nonpolar molecule have the induced dipoles, and the positive end will interact with the induced negative N with the induced positive N. Induced dipoles. Sorry. Here we have just two nonpolar molecules. And when they come into contact with each other, electrons move, and we get induced dipoles. This is a very weak interaction. Between 1 and 10 kilojoules per mole. But this is one that can, and the other ones, it can kind of ripple out. So as one molecule gets an induced dipole, it can induce another one, which can then induce another one, and it goes on and on. So large scale, it becomes a little bit stronger. So we're thinking about our dispersion forces or our London forces. There are some things that are going to affect the strength of those dispersion forces. So we're talking about the movement of a sea of electrons. So the more electrons, the more we can move that sea, right? So the greater the number of electrons, the more it can be pushed in one direction or another, creating a larger induced dipole. So if we have a nonpolar molecule, or even a polar molecule, the greater our intermolecular, or the greater our molecular weight, the greater our London forces. So if we have something like methane versus dodecane, much greater molecular weight, much greater London forces. I'm just going to do LDF for London dispersion force because I'm being lazy. Another thing that is going to affect our London dispersion forces is our surface area. So the greater our surface area, the greater our London dispersion forces. We can kind of think about this like a marble versus a spaghetti, a thing of spaghetti. So if we have a spaghetti noodle, it's long, has lots of surface area, it gets stuck to the other spaghetti noodles very well. If we have a bunch of marbles, they don't get stuck very much. So the greater our surface area, the kind of more directional you can push those electrons, and the greater the London dispersion forces or induced dipoles that you will have. Like I said, more interactions between your molecules, and then more directionality to the movement of the electrons. So a way to look at kind of the London dispersion forces is through something called polarizability, which is the ease at which an electron cloud of an atom or molecule can be distorted by an outside force. So something that is polarizable is something that can easily get its electrons pushed in one direction or another. So if we look at fluorine, F2, versus iodide, I2, we see that fluorine gas versus iodine gas, fluorine has fewer electrons. Those electrons are held closer to the molecule. So they're not as free-flowing as the electrons in something like iodine. Iodine has electrons that are further away from the molecule. Remember our strong nuclear force, or our effective nuclear force. So iodine would be said to be significantly more polarizable than fluorine. Same thing can happen when we've got larger molecules. So something that has electron that is easily distorted, causing an induced dipole, is said to be polarizable. And this causes an induced dipole. So big spongy molecules, more polarizable, and will have greater dispersion forces. So our LDFs, our lead dispersion forces, are going to be greater. So take fluorine versus chlorine versus bromine versus iodine. We look at fluorine. Fluorine has not very polarizable, so it's going to be a gas at room temperature. Same thing with chlorine. Chlorine's a little bit larger, but still a gas at room temperature. Bromine, much larger. It's going to be a liquid at room temperature. And then iodine, significantly larger, is a solid. So we can look at polarizability and states of matter, and it does in fact matter. Okay. Next thing we want to look at real quick is just surface area and molecular weight. So if we look here at this table right here, as we go down, we're increasing our molecular weight, and as we go from right to left, we're increasing our surface area. And we can see this molecule over here has the greatest molecular weight and the greatest surface area, giving it the largest boiling point. So a lot of our properties, including whether it's what state of matter it is, its boiling points, its melting points, and some other properties we'll talk about in a little bit, are very dependent upon the intermolecular forces that exist. So here we have a nonpolar molecule. That nonpolar molecule is a fairly high boiling point molecule because it's got a large molecular weight and a great surface area. As we compare, these have the same molecular weight, these two right here, but because one is in a line, the other one's kind of more ball-shaped, we have a lower boiling point. So again, as we increase that surface area, as we increase that molecular rate, we're going to have significantly increased boiling points and melting points. So we'd say that boiling point is an indicator of the strength of the intermolecular forces. Okay. So let's think about dipole versus dispersion forces. There are polar molecules, as I said, exhibit dispersion forces. So when we're trying to think about intermolecular forces and we're ranking or determining what intermolecular forces kind of take precedence within the molecule, we have to look at sizes and our dipole-dipole interactions and our electrostatic interactions to determine what force is going to be dominant within a substance. So if we have two molecules that are similar in size and mass, then our dipole-dipole interactions are going to be a more dominant force. So the dipole-dipole forces will always win out if we're similar sizes. So we have a polar molecule, non-polar molecule, intermolecular forces are always going to be greater in the polar molecule if they're similar size and mass. Now, the larger our molecule gets, the more dispersion force becomes the greater or the dominating electrostatic interactions. So we will get to a point where we have a molecule that is large enough that dispersion forces will become the dominant intermolecular interaction or electrostatic interaction. Okay, so we've talked about all of the different intermolecular forces except for one. Last one we want to talk about is hydrogen bonds. So hydrogen bonds a lot of times are considered a super strong dipole-dipole interaction. So this occurs when we have a highly electronegative atom bound to a hydrogen atom, which has a very low electronegativity. So our high electronegative atoms are nitrogen, oxygen, or fluorine. hydrogen that's attached to a nitrogen, oxygen, or fluorine produces a very, very polar bond. So much so that hydrogen is almost, the electron density pulled away from that hydrogen so much that it's almost lost all its electron density. So as such, it wants more electron density around it. And what happens is an electron pair from a highly electronegative atom will interact with that hydrogen attached to a nitrogen, oxygen, or fluorine. So we have to have a substance that has a nitrogen, oxygen, or fluorine bonded to a hydrogen, and that nitrogen, and then we have to have a nitrogen, oxygen, or fluorine that has an electron pair. So our pair of electrons on our oxygen, nitrogen, or fluorine is going to hydrogen bond with a hydrogen attached to an oxygen, nitrogen, or fluorine. So we have to have those two things. This is a strong force, not as strong as ion dipole, but stronger than traditional dipole-dipole forces. So it kind of fits in between those two. Again, two criteria. We have to have a hydrogen attached to a nitrogen, oxygen, or fluorine, and then we have to have a nitrogen, oxygen, or fluorine that has an electron pair. Now, both of these things can be found in the same molecule, or they can be found in two different molecules. So if we have a mixture, we have one molecule that has a hydrogen attached to a nitrogen, oxygen, or fluorine. We have another molecule that is a nitrogen, oxygen, or fluorine that has an electron pair. Those two can come together to produce a hydrogen bond. We just have to have those two criteria. Lone pair on nitrogen, oxygen, or fluorine, hydrogen on nitrogen. Okay, let's continue on talking about our hydrogen bonding. So one of the things that really exhibits hydrogen bonding very well is DNA, deoxyribonucleic acid. So with our deoxyribonucleic acid, we have the structure that we see over to the right. So we have a double helix, and that double helix is held together by hydrogen bonding. So you may know or may be familiar with the base pairs that form thymine, adenine, guanine, cytosine. So those are specific. We only have those base pairs that form within DNA. And the reason for this is because the location and amount of our hydrogen bonds within those structures. If we look at thymine and adenine over here, right here, we can see that they both have two positions where they can accept or donate a hydrogen bond. So thymine has this oxygen on top. This oxygen has a lone pair of electrons, which hydrogen bonds with the hydrogen attached to nitrogen on adenine. Then this nitrogen below on thymine has that hydrogen that will hydrogen bond with the nitrogen with a lone pair on adenine. Same thing with guanine. With guanine, however, we have three spots for our hydrogen bonds. We have oxygen hydrogen bonding to a hydrogen attached to nitrogen on cytosine. Then we have our guanine with this hydrogen on nitrogen, hydrogen bonding with the nitrogen on cytosine, and then again hydrogen on nitrogen on guanine, hydrogen bonding with electron pair on oxygen on cytosine. So our DNA, double helix, is held together by hydrogen bonds. And like I said, thymine and adenine both have 2 hydrogen bond locations, while guanine and cytosine both have 3. Hydrogen bond locations. Where location, I'm talking about either a hydrogen bond acceptor or a hydrogen bond donor. So let's look at our learning goal, or learning objective number 2. So concept check. So we should be able to, at this point, tell all our different types of intermolecular forces, and we should be able to rank them as well. So our very strongest of all of our intermolecular forces is an ion dipole. So we're going to put that as 1. So our very strongest. Our next one after that is going to be hydrogen bonding. Hydrogen bonding is very, very strong in reference to intermolecular forces. Then after that, we've got our dipole-dipole. And then lastly, our London dispersion forces. And remember, with our London dispersion forces, we have ion dipole, or sorry, ion induced dipole rather. Dipole, induced dipole. And then our weakest of all our intermolecular forces will be our dipole-dipole, or induced dipole-induced dipole. Thing I want to note is some of these can only exist in mixtures. So our ion dipole, our ion induced dipole, and dipole induced dipole. These are only in mixtures. All of them will exist in mixtures. Hydrogen bonding is in mixtures, dipole-dipole is in mixtures, and our induced dipole-induced dipole is in mixtures. But those 3 specifically are only in mixtures and no pure substances. So let's think about the strength of those intermolecular forces real quick. So if we have 2 substances that have comparable molecular weights, comparable shapes, our dispersion forces will be approximately equal within the 2. Okay. What about when we have substances that differ wildly in molecular weight? So if we have one substance that is very heavy, one substance that is very light, then our dispersion forces are going to weigh out as the strongest intermolecular force. So dispersion forces will become the dominant intermolecular attraction. Intermolecular force. If we have, again, substances that are equal mass, same size, the strength of intermolecular attractions will increase with increasing polarity. So increasing polarity, I'm talking about when we have substances that have greater dipoles. So larger change in electronegativity, for instance, within the bonds. And then the greater the number of hydrogen bonds, the greater the intermolecular forces holding those molecules together. So a greater number of hydrogen bond locations for donation. Or for accepting hydrogen bonds. One more note about hydrogen bonding. This one up here, not always true for substances with hydrogen bonding. We have something that has hydrogen bonding, it almost always is going to outweigh everything else as the dominant intermolecular force. Okay. So let's just look at our intermolecular forces compared to our intramolecular forces. So our covalent bonds, or sorry, a covalent network up here. So we're going to be talking about this in chapter 12, but when we have things that have extended structure, such as carbon, so think about graphite or diamond, our covalent networks are very, very strong. And then we have ionic bonds, and then under here we have our covalent bonds. And then our metallic bonds, then we have ion dipole, hydrogen bond, dipole, dipole, and then our London dispersion forces. The covalent bonds also could be here. It can kind of be anywhere depending on really the polarity of the bond, the length of the bond. We have many different, a pretty large range of energies for those covalent bonds. Okay, so let's look at how we determine what the dominant intermolecular force is. So we can ask ourselves, are ions involved? The answer is yes. Then we ask, are polar molecules involved? The answer is yes again. We have an ion dipole. The answer is no. Are nonpolar molecules and ions both present? No, we have ionic bonding. Yes, we have ion-induced dipole. If there are no ions involved, we look at whether or not we have polar molecules. If the answer is yes, or if we have nonpolar molecules, are there polar molecules? Then we have ion-induced dipole. No, then we just have London forces. If there are no polar molecules, we need to ask, are hydrogen atoms bonded to nitrogen, oxygen, or fluorine? If the answer is yes, then we have hydrogen bonding, and if the answer is no, we have dipole-dipole. So just kind of flow chart to get you started in looking at what type of intermolecular forces exist within our molecules. Okay. Another concept check, make sure we know what's going on. Let's look at some of these and determine what our dominant intermolecular force in these pure substances or mixtures are. N2, hopefully remember, is nonpolar. So if we have a nonpolar substance, anytime we have nonpolar substance, the only thing that we can have is London dispersion. Water, H2O, structure like this. This is a polar molecule, but more importantly, it's a molecule that has oxygen-hydrogen bonds. So we have oxygen and hydrogen attached to each other. We have oxygen with an electron pair on it. So within water, we have hydrogen bonding. Okay. Next, we have heptane. Heptane, if we look at this, all carbon and hydrogen bonds. If we recall, our carbon-hydrogen bonds are nonpolar, so we have a nonpolar substance. The only thing that is available is London dispersion. Now we're moving on to mixtures. Water and sodium chloride. Water is a polar substance that exhibits hydrogen bonding, and then sodium chloride is an ionic substance. As such, since we have ions and we have a dipole, we have ion dipole. And then lastly, we have N2, which is nonpolar, and water, which is polar. So this would be our London dispersion dipole induced dipole. Now, if we want to rank these from strongest to weakest, where strongest is going to be 1, weakest will be 5. We look, our very strongest force here is going to be our ion dipole. So be a 1 there. And then beyond that, we have hydrogen bonding. So 2 there. And then we move into our dispersion forces. So as far as dispersion forces go, our strongest one is going to be dipole-induced dipole. And then we have the 2 that are just induced dipole, where heptane, since it's larger, will have stronger intermolecular forces versus N2, which is much smaller. Okay. Last thing we want to look at within this lecture is going to be other properties of liquids based on intermolecular forces. One of these is viscosity. Viscosity is the resistance of a liquid to flow. So if you've ever seen anything that kind of just like slimes down, such as these oils over here, like this one right here, that is what we think about as something that's viscous. The SI unit for viscosity, and there is an SI unit. Hopefully you guys remember your SI units. It's going to be kilograms over meters times by seconds. Okay, so generally, the greater your intermolecular forces, the greater your viscosity. So you might be thinking, water has really strong intermolecular forces, but not a lot of viscosity, right? Water is not a very viscous substance. Well, yes, greater intermolecular forces leads to greater viscosity, but that is not the only thing that is going to play a role. We also have basically the tangleability of substances. So if we have things that have very large surface area, we're going to have greater viscosity. So there's another thing that's going to play a large role is the viscosity of the substance, or the shape and flexibility. So, talking about the likelihood of entanglement. So if we have something, again, let's think about the pasta. If we have a big pasta thing, it's really hard to pull those apart, a big pasta noodle. So yes, intermolecular forces play a role, but mostly it's going to be the tangleability or ability to entangle within each other. Thing to note, our viscosity is going to decrease with increasing temperature. Okay. Some examples of some things that we see over on the right. Syrups are generally very viscous. Oils are fairly viscous. With syrups, we've got a lot of hydrogen bonding. With oils, we've got long nonpolar chains that can tangle. Okay. Next thing we want to look at is surface tension. Surface tension is the elastic tendency of a fluid surface, which makes it acquire the least possible surface area. So water is really good at this. For instance, if you've ever seen so water will kind of bead up on itself. Specifically, if we make a water droplet. So a water droplet itself is, the shape of it is due to surface tension. So this surface tension itself is an imbalance in intermolecular forces. So if we have something that really likes itself, it's going to try and drag itself in. It's one of the reasons that things can kind of walk across water, like bugs. So water molecules, for instance, will draw other water molecules in, making your surface smaller than normal. What it is with our hydrogen bonding. So if we look at this picture over the right, we can kind of get an idea of what happens. So with our surface water molecules, what happens is they are being pulled more from the inner water molecules, than they are from the top. So it kind of draws everything down. You can also see down here in the picture on the bottom right, we can see how surface tension, if we have a substance, a non-wettable substance, so that's something that has a different intermolecular force than water. So for instance, a non-polar substance, the water will kind of bead on that substance, increasing your surface tension. Here are some pictures exhibiting surface tension. So if we have something like a bug walking across water, or a water droplet form, that's due to surface tension. So the surface is, or the water likes itself more than the surface it's on, so it's going to kind of decrease its surface area so it has more contact with itself versus the thing it's in contact with. So this allows for things to float on water despite being more dense than water. And it causes water droplets to form. Okay. Very last thing we want to look at is capillary action. Capillary action is cohesive and adhesive forces at play. So cohesive is the tendency of a liquid to resist separation. Adhesive, attractive forces between different molecules. So cohesive is usually when like molecules bind together. So water liking other water molecules. Adhesive is when a molecule likes something else, like water liking glass. So our cohesive forces are caused by intermolecular forces binding similar molecules together. And the greater your intermolecular forces, the greater the cohesive forces. Adhesive, again, is when it adheres to something else. So caused by intermolecular forces binding different molecules together. And then our capillary action is interplay between those cohesive and adhesive forces. So it'll rise up, so a liquid will rise up tube like water. Water will rise up glass because glass is a polar substance. And then it'll kind of overlap on itself again, and then rise up, and then overlap, and then rise up, and then overlap. And it'll cause that liquid to go up a tube. So we can see that capillary action over here, and the smaller the capillary, the greater the height of the liquid. So this is going to be, the capillary action is the rise of liquids up a very narrow tube. Okay, let's see how you guys are understanding our intermolecular forces. Okay, so I've got three substances. I've got water, I've got methane, and I've got vegetable oil. So we're going to look at our relative viscosity, relative surface tension, and we're going to be doing that looking at our intermolecular forces. And I've got some boiling points and melting points as kind of reference. So let's look at the intermolecular forces that exist within water. We have, of course, hydrogen bonding. That's going to be the dominant one. But it's not the only one, right? We also have dipole-dipole and London dispersion. Okay, specifically induced dipole, as those do exist within all molecules. With our methane, all carbon-hydrogen bonds, all nonpolar, so this is going to be just London dispersion. And then lastly, we've got our vegetable oil over here, and our main force, since this is such a large molecule, is going to be London dispersion, although there is some dipole-dipole. So when we compare our methane versus our vegetable oil, we see that they have significantly different melting points and boiling points. This is due to the very large size of the carbon-hydrogen chain within within vegetable oil. So it ends up, we can see here when the London dispersion forces allow us to have a substance that has greater intermolecular forces because of the length. But let's think about relative viscosity. Remember, viscosity does depend on intermolecular forces, but usually what's going to play out more is the ability to entangle the molecule. So our relative viscosity, the one that's going to have the greatest viscosity is going to be our vegetable oil. So we're going to call this 1. And then our weakest, London dispersion, there's not a lot going on because it's such a small molecule. So this is going to be the weakest here. And then water is going to be our medium one. And then surface tension is mostly due to intermolecular forces. So our strongest is going to be water. Our weakest is still going to be methane because, again, not a lot going on. And then our vegetable oil will be right in the middle. Hope this made sense to everybody. We will be discussing this in class on Thursday. So if you guys have any questions, please either email me or write them down so we can discuss them in class. And I'll see you guys soon.